looking at the metalloids, we have boron, silicon, and arsenic. And also, as I say silicon here, that makes me realize that I actually should go back a couple of slides. Actually, I just passed it. Right here. This one I identified as silicon earlier. It looks like silicon in this image. It's a little bit lustrous, but not very much, but this is actually carbon, so make sure that you correct that in your notes. So let's get back to the metalloids. And here we go. So when we combine all these elements together, and of course we know that we have a whole line of elements out here all the way up to 118 at that location. You can see sort of a color-coded look at blue representing metals, the yellow over here representing the metalloids, and this magenta color out here, pinkish color, representing the nonmetals. And we also have compounds. If you remember, we had elements that could not be, or homogeneous matter that couldn't be separated by physical means. First was element, or the first of the pure substances was elements. The second of the pure substances would be the compounds. These are pure substances composed of two or more elements combined in definite ratios. The important part is definite, and compounds are always composed directly of elements. So if we have element X and element Y, whatever they may be, we put them together, we have a mixture of the two. Something happens through here, so what we have in this case, this is a physical process here, that we just mix them. There's probably some sort of energy source involved here, and then we have a chemical change occur, which will be discussed more in the next video. And in the end, we have, for every one of the red elements, we have two of the blue elements. This is probably oxygen and hydrogen making water, but they are stuck together in the end. So what sticks those atoms together? In compounds, we have chemical bonds. Chemical bonds are forces, and specifically attractive forces that hold atoms together to make a compound. They can be very strong and very difficult to break. So very strong forces of attraction. Usually this is a major topic for later in the course. When we put the chemical bonds between the atoms and the atoms stick together in definite ratios, we have one possibility at least, something known as a molecule. Molecules are multiple atoms held together by chemical bonds, and they're the simplest unit of a compound. So as atom is to element, molecule is to compound. So atom is the simplest unit of an element, molecule is the simplest unit of a compound. So molecules follow a particular law, known as the law of definite proportions, and this just says that the individual compounds, such as water, for instance, is always composed of exactly the same elements in exactly the same proportion by mass. So, for instance, if we have something like water, H2O, we're always going to have 2 mass units of hydrogen to 8 mass units of oxygen. Let's make that 16 mass units of oxygen, and it becomes a 1:8 ratio of by mass. So by mass, 1 mass unit 8 mass units is what we get with water. Very important, and the reason we say that it's the reason I'm saying that it's very important is because one thing that this allows us to do is that we always know if we've got 1 mass unit of hydrogen. Water is always composed of 1 to 8 mass ratio. We always can say that if we have this particular mass ratio of hydrogen to oxygen, then we have water. If, on the other hand, we had something like H2O2, this would be a 2 to 32 or a 1 to 16 mass ratio, which would mean that this is not water, this is hydrogen peroxide. Okay. So very specific mass ratios, which means very specific formulas. The law of definite proportions allows us to write formulas for compounds. And we always know water is going to be H2O and it doesn't change to something else on a later date. So as I just said, putting it in more formal terms here, the law of definite proportions allows us to use chemical formulas to represent chemical compounds. Chemical formula for a compound is a constant, does not change. Okay. For compounds, the parts can't be separated by physical means, meaning that we can't filter the hydrogen or oxygen out of water. We can't filter the carbon out of sugar. They're chemically bound together, and physical means don't separate chemical bonds. So whenever compounds are broken down, which they can be, it has to be by chemical means. When that happens, bonds break, atoms rearrange, new bonds form, and we get new substances. So when compounds form, as an example, if we have hydrogen and oxygen yielding water, we had hydrogen to begin with, oxygen second, H2O2 yields H2O. Hydrogen and oxygen are unique substances. Water is also a very unique substance. Okay? If we take something and break it apart, such as SO3, and we break that apart into sulfur and oxygen, then the end result is we've got this gaseous compound here. If it's broken apart, we form solid yellow sulfur and oxygen gas. So we get new pure substances whenever we go through this chemical process or chemical change. So by chemical means chemical change. New substances are always produced during those processes. So as an example here, we have methane. Here we have oxygen. So we have 2 units or molecules of oxygen with every 1 unit of molecule of methane. This is CH4. This is O2 and O2. This is going to produce carbon dioxide and water. Okay? Very different substances on either side of the equation. All right, so suppose we have matter. We've done quite a bit with this side, the homogeneous states of matter. Let's look over here at the multiple phases or heterogeneous side of our diagram. Big difference in heterogeneous mixtures and homogeneous mixtures. So they're both mixtures, but the big difference is going to be in particle size. Solutions or homogeneous mixtures have particle sizes that are in the range of individual atoms or molecules, whereas heterogeneous mixtures have particle size that are usually greater than 1,000 nanometers in size, large enough to scatter light. And it's even possible that we can see the particles, even at their smallest. For instance, a mixture might look, if it's a cloudy, if it's a, let's say you put chalk and water or sand or dirt in water, you can see the individual particles. Some of those settle out, but then even after that, there's something left behind that seems to stay in the water, but we can tell that there's something there because of the cloudiness. So heterogeneous mixtures, as with all mixtures, can be variable in composition. The parts of the mixture can be separated by physical means, often based on particle size, so you get things like filtration. If you have an air conditioner filter or a coffee filter, the reason we can use that is because the particles that we're trying to pass through the filter have different sizes, and the larger particles, those that were in the heterogeneous component of the mixture, would be held back by, for instance, the filter. Paper in the case of coffee, or some other type of filter in an air conditioner. So examples of heterogeneous mixtures, we have a nice salad. We have a mixture of different liquids that have different densities, and the low density on top, higher density on the bottom. We have clouds in the sky. We have a sample of blood that's been separated. This would have been whole blood to begin with, and we end up having 3 different layers in the blood after it's separated. And then here we have probably a chemical process. This area down here, a term that you learned in an earlier lab, this would be a precipitate forming. So summing it all up, we have matter that exists in one phase. If it's no, we go with heterogeneous mixture. If it's yes, we have homogeneous matter. Homogeneous matter, we also can look at whether or not we can separate by physical means. If the answer is yes, then we have mixtures. If the answer is no, then we have pure substances, which could be either elements or compounds. And that concludes this lesson.